So here we're going to talk about increasing and decreasing functions. This is section 3.3. In 3.1, we were concerned about the critical numbers. Okay, if you recall, critical number was whenever we had a C value that if I did f prime of C, that gave me 0, or it wasn't undefined, it did not exist, and then it would be a critical number. So that's what we were concerned with in 3.1. So like an example with this parabola here, we would have a horizontal tangent line at the vertex, so I would be concerned with just this one C value, C equal to 4 here. Excuse me. Now, for this section, we're going to want to focus on the behaviors between the critical numbers. So how does the function behave on this side of the critical number and on the other side of the critical number? And when just looking at it, all right, so from definition, a function f is increasing if, well, x1, okay, so I'm going to have increasing, and just looking at the graph, I know this side is the side that's increasing, right? So I can probably make some guesses on this, but let's not guess, let's just do it, right? So I have an x1, and I have less than x2, so I'm just going to pick an x2 that's a little bit bigger than x1, all right? And so if this is the case, then what do I know about f of x1? Well, I take x1 and I plug it into my f graph here, and it outputs there. And then I take my x2 and I plug it in for f, and it outputs there. How do these 2 points relate to each other? Well, clearly you can see that f2 has a higher value than f1 does. So f of x2 is greater than f of x1. All right, so this is the case. If x1 is less than x2, then f of x1 is less than f of x2. Okay, makes perfect sense. My inequalities go the same way here. And that would be increasing as we move further to the right. As my x values get larger, my y values get larger. That's the idea, okay? Direct relationship going on there. Now, when I think about slopes of tangent lines going up like this, I'm thinking the derivative evaluated for any x value on this side, that derivative we know is going to be positive. Okay, so we're going to use that fact later. Next, I have to define what decreasing is. So it's the opposite of increasing. So you know from college algebra that we're decreasing on this side of the parabola. Well, the old algebra definition is if I have x1 less than x2. Okay, well, what does that tell me? The output of x1 is greater than the output of x2. Okay, clearly you can see that dot right there is higher than that dot there. So f of x1 is greater than f of x2. All right, so it's like the reverse relationship going on here. As your x's get bigger, your y's get smaller. Okay, so with increasing, it's direct correlation here. As x gets larger, y gets larger. With decreasing, as x gets larger, the y values, the outputs get smaller. Okay. Now, what do I know about the derivative on this side? Well, the derivative looks like it's a slope going downhill, so that's a negative derivative. Okay. So critical numbers allow us to break up the function into increasing and decreasing parts. What do I mean by that? So say I have, with this graph here, all right, I have a critical number right there, okay? I know on this side over here that I'm decreasing. The function is decreasing. The critical number separates me from the decreasing to the increasing side here, okay? So you can see from this graph here that the critical number breaks up, in quotes, the function into increasing and decreasing parts. That's what I mean by that little statement there. All right, so let's talk about relative max, and then we'll talk about relative min. So when we have a relative max here, okay, as my x's increase, what's happening here? Well, the value of the derivative is what? It looks like the value of the derivative is positive here. Once we get to the maximum, what do we know about the derivative here? The slope looks like it's a horizontal line, so that slope is 0, so the derivative is equal to 0. And then coming down the hill this way, looks like our derivative turns negative. So relative max, what's happening? I go from positive to 0 to negative. So if my derivative goes from positive to 0 to negative, then I have a relative max by this picture, right? What about the relative min? Well, it's the exact opposite. Okay, the minimum's located right here. As I'm heading towards it, what is this? My derivative is negative. Okay, it's negative. And then what happens? Once I get to the minimum, we get 0. And then it becomes positive. It becomes greater than 0 over here. So what's happening? The derivative, f prime, goes from negative to 0 to positive. So if I see a scenario where my inputs, whenever I plug the numbers in, I get a output for a derivative negative, then I get an output for 0, then I get an output for positive here, then that's a great indication that I have a relative min there, okay? Remember, the critical numbers where the derivative is equal to 0 or does not exist, all that does is break up our function between increasing and decreasing parts. It's increasing here, decreasing there. It's decreasing here, and then increasing there. Okay? So this kind of sums up everything that I'm trying to say here. This is a theorem, and we'll talk more about this in another video. But 3.3.1, test for increasing, decreasing functions, all right? So let f be continuous on the closed interval and differentiable on the open interval. So this is a very common assumption here in this chapter of calculus, having a function that's continuous and differentiable, okay? Very nice things happen when that's true. Now, if f prime of c is greater than 0, where c is between a and b, okay, so c in a, b is a fancy way of saying if I have a and I have b, then c is somewhere stuck in between, okay? So on your interval from a to b, I just pick a random c somewhere in there, and I don't know where it is, so it's like I can move it all around as long as it's stuck between a and b, okay? So that's all that is. Anytime you see this phrase here, that's what we're talking about for all C and AB. All right, then what does that mean? So that means the derivative is positive on A to B. Then what do we know? Well, if the derivative is positive, what does that mean for us? The derivative positive means that we're increasing, okay? Now, what about the derivative negative? If the derivative is negative on AB, what does that tell me? Well, if the derivative is negative, I'm over here, right? So derivative negative is over here. And so that means that I'm decreasing on the interval, okay? And if the derivative is equal to C, or the derivative evaluated at C is equal to 0 for all C and AB, then the function f is constant on AB. Now, there's an issue going on here, okay? And so something I want you to take note of, all right? The derivative is only equal to 0 at one point for both of those there. 1 point does not make an interval. You don't write a comma a. You would never write that. You wouldn't write like if this was like an x equal to 4 value here, you wouldn't say 4 comma 4. What you would say is the set 4. Okay, so it's only one value. So this constant only works when we're talking about like an interval there, okay? We're not talking about an interval for this particular picture. This would be like a scenario like this. Maybe I have some function that comes up like this, and then it goes across constant, and then maybe it comes down like that, okay? So what do I know? Well, the derivative is positive here. It's increasing, right? So if the derivative is positive, we're increasing, okay? And then over here, my derivative is negative. The derivative is negative, we're decreasing, okay? And then last, if the derivative equals 0, like here, the derivative is horizontal, its slope of the tangent line is 0, then we have a constant function. So I just wanted to point that out to you. At the vertex of a parabola, like this example here, where we have relative max and mins, we do not see, we don't say, hey, the function f is constant at 4, okay? We don't say that. The function is constant on an interval, and a single point does not make an interval.